Alrighty, yesterday you had your chapter 5 quiz, so today we are going to go over the chapter 5 quiz, and then I'm going to move on to 3.1, which you already took notes on. So, number 1 asked us to show off our knowledge of the quantum mechanical model by using it to explain how neon lights work. So, I am going to give you the topics or the pieces of information that you needed to include in order to get these 4 points. So first you needed to, whoops, that's too fat. First you needed to explain, you could have, if you wanted to, you could have explained the quantum mechanical model and then explained how neon lights work, or you could have explained how neon lights work and incorporated the quantum mechanical model in there. But either way, you needed to have these 4 main bullet points, and then how much you expounded upon those determines how many points you got. So you needed an explanation of the structure of a neon light. So you needed to talk about the glass tubes, the atoms of gas within the glass tubes, the electrons within the atoms, and what happened, and the electric current that is put through this glass tube. Then you needed to talk about what happens to the electrons in these atoms that are in this glass tube. Remember that when the electrons are bombarded by an electric current, they gain a certain amount of energy called a quantum. And they all exist in their ground state, which is their principal energy level that they're most stable at. They exist at their ground state. When they absorb this electrical current energy, they jump up to an excited state or a different principal energy level. So I was really looking for you to talk about principal energy levels and that amount of energy being a quantum to go from one to the other, to show that you understood how the quantum mechanical model was incorporated into neon lights. Then I needed you to explain that when these electrons emit this quantum of energy after they've absorbed it, they are actually emitting a visible wavelength of light, and that is what gives the unique atomic emission spectra. You didn't need to mention the atomic emission spectra, but if you did, bonus points. But you did need to discuss the uniqueness of these elements and their electron configurations is what determines what color light the neon light gives off. So if you covered all those things, you probably got 5 out of 4 or 6 out of 4 on that question. Okay, number 2. Number 2 says a wave of light has a frequency of 4.2 times 10 to the 11 hertz and a wavelength of 7.14 times 10 to the negative 3 meters. And I want to know what type of electromagnetic radiation this is. So what we need to do is look at, what is it? I'm going to write 4.2 times 10 to the 11 hertz is my frequency, and I have a wavelength of 7.14 times 10 to the negative 3 meters, and that is my wavelength. I'm just writing this down because I have to scoot. Oops. Cut this, bring over here. Okay, so this is our information. We needed to use this supplemental material on the last page of your quiz in order to figure out what type of electromagnetic radiation this is. So we need to use the electromagnetic spectrum in order to do that. So first, let's look for our frequency, 4.2 times 10 to the 11. So all you really need to do here is look at the 10 to the 11, or sorry, the exponents here. So here we have 10 to the 10, and here we have 10 to the 12. So 10 to the 11 is right in the middle there. So somewhere in microwaves it looks. And to verify this, we would look at our wavelength, which is 10 to the negative 3. Well, conveniently enough, we have 10 to the negative 2 and 10 to the negative 4 here, meaning 10 to the negative 3 would fall perfectly in the middle of that. So I see that I am in the microwaves region of the electromagnetic spectrum. So that would be my answer for number 2. The type of electromagnetic radiation, whoops, I'm writing electromagnetic radiation, is microwaves. All right, next part. Could this electromagnetic radiation be from an atomic emission spectrum? Why or why not? The answer would be no. It could not be from an atomic emission spectrum. The reason for that is because electrons only emit, let me erase all this stuff. Electrons only emit wavelengths of visible light, wavelengths and frequency of visible light. And the frequency and wavelengths of visible light are all the way up here. And we're in microwaves. Microwaves are not an example of visible light. Okay, so the answer would be no, and something along the lines of what I just said. Electrons emit electromagnetic radiation within the visible light spectrum. All right, so something along those lines. Obviously, you don't have to write the visible light spectrum or something that. If I can understand that you understood that no, microwaves would not be a part of an atomic emission spectrum, then you got full points for that. So you got a point for the no and a point for the explanation. Alrighty, next we had this problem where you needed to match the element with the correct electron configuration. So what I would do first, if I was you, I would have looked at the periodic table and determined how many electrons. So if I want to figure out which one of these is potassium, it actually might have been easier to count all the electrons in this one, and this one, and then work on the shorthand ones. So let's do that first. Remember that these little, let's zoom in here. These little numbers, we're going to do B first. These numbers, the exponents, as some of you call them, or the superscripts, they indicate the number of electrons. So here we have 2, 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, 20. We have 29 electrons in this one. So from there, I would have gone to my periodic table and looked at which element had the atomic number of 29. That is copper. So this must be copper's longhand electromagnetic, or excuse me, I keep saying the wrong word, electron configuration. Then I would have done the same thing with this. This has 10 plus 3 is 13 plus 6. This one has 19 electrons. If you look at the periodic table, the element with an atomic number of 19 is potassium. So potassium is D. And finally, with this one, we have 10, 20, 28. 28 electrons. And looking at the periodic table, we see that that one is nickel. So that's E here. So that leaves us with chlorine, strontium, and krypton. I would do krypton next. But I mean, it's fine however you did it. But I would do krypton next. You probably, maybe you could just look at the, actually if you just follow these directions, let me pull up a periodic table here. All right, if we just follow the directions, let's just do this one first. We'll do A first. So we go to neon, which is right here. And then we're going to go to the next row. We're going to go to 3s2. So we go down from 10. We're going to go to 11, and we're in 3s1. Here's 3s2. And then we go to 3p5. Right? So we go 1, 2, 3, 4, 5. We find that this is chlorine. You could have also just written the shorthand for chlorine if you wanted to. Okay, then we have strontium. We can do it the opposite way this time. Strontium's shorthand electron configuration, if we go backwards from here, we are at 37. That's not a noble gas, so we need to go to the next noble gas, which is 36. So we're going to have Kr, krypton. All right, then where are the last 2 electrons of strontium? They are in the 5s1 and the 5s2. So we would have krypton, 5s2, and that is letter C. And finally, we have krypton itself. The electron configuration, the shorthand for krypton. Krypton is right here. We have to go all the way backwards to number 18 to get our last noble gas. That's argon. Then we have all of these in the middle. We have a, what is that? 4s1, 4s2, 4s2. Then we have 3d10. Then we have 4p6. And conveniently enough, that is letter F there. So there are the answers for number 3. All right, what is the main difference between Bohr's model and the quantum mechanical model? Remember that Bohr had 3 postulates that are postulates or components of his model. You didn't need to discuss this, but I'm just giving you some. If you had a hard time figuring this question out, you could have thought of the 3 components and then narrowed it down. Remember, the only one that wasn't true or that isn't associated into the quantum mechanical model now was his component that said that electrons orbit in like planets in circular paths. Remember? In circular paths. That's what Bohr said. And remember that the quantum mechanical model actually shows us that electrons are in a cloud. 3-dimensional cloudish structure, right? So they're in a 3D cloud spinning around the nucleus. And that is the main difference between these two, because quantum mechanical model actually incorporated the other 2 components of Bohr's into itself. That electrons are in fixed principal energy levels, and they can move up or down between the principal energy levels by emitting or absorbing a quantum. So, if you said something along these lines, obviously you needed to use full sentences, then you're good to go with that one. Moving on to number 5. All right, number 5 asks us, what color of light does lithium emit? Well, we look at this atomic emission spectra, and we see that it's mostly red and a little bit of orange. So if you said red, you got the point. If you said reddish orange, you also got the point. If you said yellow, you did not get the point. If you said blue, you did not get the point. Red or reddish orange got you a point for that. Then it says, circle the most reasonable range of wavelengths that lithium emits. So for this, we needed to look at our electromagnetic spectrum, or yeah, that's what we needed to look at. So let's look at that over here. So here, this depends on what you answered for part A, but anything between between like 625, or even if you said 650 and 750, that would have been good. So let's look at our answers over here to see which one of those matches up. Well, this doesn't make sense because it's the entire visible light spectrum. This is violet and this is red. There is a good looking answer, but let's go through the rest. 550 to 625, 550 to 625. Well, 625 would have been good, but this is not reddish orange colored light, so that one can't be it. And then 380 to 500, 380 to 500 would also not have been orange or red colored light. So the correct answer here is number 2. All right, and then letter C says that the main frequency of electromagnetic radiation coming from a, quote, neon light is 5.54 times 10 to the 14 hertz. I wanted you to find what is the wavelength of this light, and your answer had to be given in nanometers. So we are given the frequency, which is equal to 5.45 times 10 to the 14th. And maybe you thought, well, I'll just look over here at my electromagnetic spectrum. We're at times 10 to the 14th. So it would be somewhere around here, but the problem is we don't know exactly what the wavelength is. And I'm asking you specifically to tell me the wavelength. If you gave me this, that is wrong, because I gave you an equation. We went over an equation that c, which is the speed of light, equals wavelength times frequency. So I know the speed of light. I gave it to you in the supplemental materials. It is 2.998 times 10 to the 8 meters per second. If we rearrange this equation to solve for wavelength, we would divide both sides by frequency, and we get that wavelength equals speed of light divided by the frequency. So then we just need to plug in these two values that we have here and solve for our wavelength first in meters. Remember, to make this simpler, remember that another way to write hertz is per second. So we'll write per second, and we're going to do that so that my seconds and seconds cancels and I'm left with the correct units. So let's do it. We have wavelength equals 2.998 meters per second divided by 5.45 times 10 to the 14th seconds. Oops, per second. Per second. All right, when I do that, when I plug that into the calculator, where is my answer here? I get, I wonder if you saw that I forgot to write times 10 to the 8th there. Times 10 to the 8th meters per second. Okay, when I plug that in, I get 5.5 times 10 to the negative 7 meters, because my seconds and my seconds cancels. All right, but I'm asked to report this in nanometers. So you could do dimensional analysis and say how many nanometers equals 5.5 times 10 to the negative 7 meters. I know that 1 meter is equal to 1 times 10 to the 9th nanometers. I cancel my meters and my meters, and I get 550 nanometers. That was the correct answer for this one. Alrighty, 550 nanometers is the main wavelength of light coming from this, quote, neon light. And I put it in quotes. You know why I put it in quotes, because it's not necessarily neon, right? All right, part 2 of letter C asks, which of the elements in the atomic emission spectra diagram is associated with this frequency and wavelength? So we look up here, and we already looked at the frequency on our electromagnetic spectrum, and we know that we're somewhere around here, right? So we know we're in visible light, and we know that 550 meters is the wavelength we're looking at. So if we go look at this one, 550 meters is some kind of greenish yellow, okay? If we look at our atomic emission spectra here, we see that boron would make the most sense. I heard that some of you didn't remember what B meant, and I hope that Miss Eno I'm sure she made the point clear that you have to know that you have to know the symbols on the periodic table. This is chemistry. Not knowing the symbols on the periodic table is like not knowing the letters of the alphabet in English. You have to know these things, okay? So the correct answer for that would be boron. All right. Okay, maybe I gave you, I can't remember on this one if I gave you a bonus point. If you just wrote B, you got it correct. But if you wrote boron and you flexed your muscles, then I think I gave you half a bonus point or something. All right, moving on to number 6. Number 6 asked you to provide the electron configuration diagram for each of the following. All right, we did lithium first. Let me pull up my periodic table here. We are looking right here at lithium. Lithium has 3 electrons that we need to place. The correct electron diagram would have been 1s2, 2 electrons. Moving up to the next would be 2s1. There we go. To double check, it has 3 electrons. We count the superscripts. That is 3. Good to go. All right, so you got points. These were each worth 2 points. You got points for writing this part correctly, and you got points for filling in the arrows correctly and having the correct orbitals. Oxygen is number 8, so we have to figure out where we're going to put these 8 electrons. We start with our lowest principal energy level, which is the 1s, and we fill that up, 1, 2. Then we move on to the 2s. Oops, I forgot 2 there. 2s, we do 3, 4. There we go. Then we move on to the 2p orbital, and we have 4 more electrons to place in the 2p orbital. So we know that it's going to have 4 electrons. Now we just have to figure out how we're going to put them in. We have, because of our 3 rules, the Hund's rule and Pauli's rule, and we already have followed Aufbau's principle, so we're going to follow the Hund's rule right now. We're going to put them all up first. So we have 3, then we have 4. There we go. That is the electron configuration diagram for oxygen. Next we have beryllium. Beryllium is right here, number 4. So we have 4 electrons we need to place for beryllium, 1s2, and, 2s2. Finally, neon is number 10. So we have 10 electrons we have to place for neon. We'll put them first in the 1s and then in the 2s. We have 4. Then we will move on to our 2p. We have 1, 2, 3, 4, 5, 6 electrons in the 2p. This, all counting them all together, we'll see we have 10 electrons here, and we are good to go. Done with that. Finished. Over. All right. Number 7 wanted you to rank these 4, lithium, oxygen, beryllium, and neon. We needed to rank these 4 elements from the most energetic, or the least stable, to the least energetic, aka the most stable. And I forgot a parenthesis. Oh, dang it. I thought I made no mistakes and I forgot a parenthesis there. Anyway, okay. And you need to give a justification for each ranking. So, if we look at our 4, we want to write the least stable element first. Remember, we have this concept of filled being the most stable, aka the least energetic. Oh boy. Then we have half filled is the middle. Remember, medium stability, medium energy, and then we have the partial. And this is the least stable and the most energetic. And we look at these 3 things first, and if we have a tie, for example, we have 2 partials, or 2 half-filleds, or 2 fully filled, we look at the number of electrons. And the more electrons, the less stability. So, let us begin. We have our least stable are going to be our partially filled. So let's find our partially filled, and that will be our first one in the list. So we have least. Well, if you look up at our electron configurations we did before, this one, oxygen, is the only one that has a partial electron configuration. So oxygen is going to be our least stable. And the reason for that is because it's partially filled. Partial. I'm just going to write partial. All right. That is less stable. Then we don't have any other partially filled, so we move on now to our half filled with middle stability. Here we have only one half filled, and that's lithium. So lithium is next, and the reason for that is it's half filled. Finally, moving on to our fully filled, we have 2 fully filled. We have beryllium and we have neon. So we have a tie, so we have to look at our second rule down here. Our second rule, we have to look at the number of electrons. So neon has more electrons, so therefore it is less stable than beryllium. So we would write neon here, and we would write filled, but more electrons, something along those lines, and the most stable would be beryllium. And the reason for that is filled and least electrons. All right? Something along those lines for your justification would have gotten you full points. And finally, we come to number 8. So you needed to fill in the blanks with the appropriate rules, those 3 rules that we have for writing electron configurations. All right, letter A says blank states that electrons occupy orbitals of the same energy level in a way that makes the number of electrons with the same spin direction as large as possible. That is Hund's rule. Next, part B asks or says that blank states that the electrons occupy the orbitals of the lowest principal energy level first. This is Aufbau's principle. And finally, it says blank states that an atomic orbital may describe at most 2 electrons with opposite spin. That is Pauli exclusion principle. All right, there you go. I will get your grades back to you as soon as possible. Hopefully by Friday, I'll get them back to you. Okay? All right, so now we are going to move on to 3.1. All right, so this next section, we're going to be covering 3.1. We're going to cover it in 2 parts. Then we're going to move on to chapter 6. So your next quiz will cover 3.1, which is about using and expressing measurements. And then we will move on to chapter 6. So we are going back, you'll notice, to chapter 3. And I think you probably remember when we got to chapter 3, we skipped it. And the reason for that was we had just spent a lot of time doing dimensional analysis, and I didn't want to overwhelm you with just all of this math and these rules. I think it's better to break it up, do dimensional analysis, apply that a little bit, and then go back and add these 2 new concepts that we need in order to write expressions and measurements in chemistry correctly. So we have 2 important things that we need to learn now in order to write our values in chemistry going forward. The first thing is scientific notation, which most of you, all of you should already kind of have a little bit of knowledge about that. So hopefully this is part 1. We're going to cover scientific notation. Hopefully this is a review, and you've done it in math classes, but we're going to need to write this, be able to write things in scientific notation going forward. And secondly, we're going to cover this concept called significant figures. Significant figures. All right, so these 2 concepts, when we're writing measurements in chemistry, are critical. And just like dimensional analysis, we already did dimensional analysis, but I'm going to write that up here. This is kind of going to incorporate, it's going to make dimensional analysis make a lot more sense, I hope. All right. Not a lot more sense, but a little more sense, hopefully. Okay, so we're going to go over scientific notation first. So let's begin. Scientific notation. We have measurements, and they are fundamental to experimental sciences, meaning we've already seen this. Like if I say 100, what's something we've said? We've said 12 grams, right? We've said, looking at all of these different things that we've done in chemistry with all of our different measurements that we've taken and looked at. We've looked at 12 grams, or we've looked at 35 AMU, right? We have all of these different, we have liters, we have meters, we could have 12 liters, we could have 12 meters. We have all of these different measurements that we have to be able to express correctly, and to be sure that they're accurate. We have to be able to write these things correctly in chemistry. So specifically in chemistry, we have very large and very small quantities. For example, the very nice example your book uses is that a single 1 gram of hydrogen contains this many atoms of hydrogen. So this is just one example. 1 gram of hydrogen contains, I can't even say this number, that many atoms of hydrogen. So in 1 single gram of hydrogen, there's this many atoms of hydrogen. Another example, one single atom of gold, how much does that weigh? What is the not how much does it weigh? What is the mass of this single atom of gold? All right, it contains how many? 21 zeros, then 327 grams. So one single atom of gold has this mass. So you see, the reason I'm writing these big, huge numbers for you is because in chemistry, we deal a lot with either super massive numbers like this one, or with super teeny tiny numbers like this one. And it can be super easy to make mistakes when we're writing numbers like this. Even if I say 153,000, if we're dealing even with something 3,000, even dealing with something like this, if we're doing calculations with this number over and over and over again, it can be very easy to lose track of one of these zeros on accident, okay? So even writing something like that, it also just doesn't look as pretty, right? It's just a lot of zeros, it's a lot big calculations. So what we use scientific notation heavily, a lot, often, all the time in chemistry. So scientific notation is a number written as the product of 2 numbers, and those 2 numbers are a coefficient and a 10 raised to a particular power. So there's that definition. You already wrote this in your notes. Some of you only wrote the highlighted words from this reading in particular, and you got a really bad grade for that notes section. But anyway, besides the point, I left you enough comments about that in the comment section on these notes. So this is what a scientific notation is. So if we wanted to let's first write this number here. We'll write this number here in scientific notation. So that number I can't even say. So if I wanted to write this number in scientific notation, what I do is I have the decimal point here, right? And I'm going to move it over so that I just have the actual numbers in my number. That's going to be my coefficient. So let me just write it. It's going to be 6.02 times 10 to the 23rd atoms. All right, that's how I write this in scientific notation. How did I do that? Well, what I've done is I've moved this decimal. There is a decimal there. We don't write it because there's nothing after the decimal, right? So we don't need to write anything after the decimal. And we don't need to write the decimal at all. We don't. But there is technically one here. So if I move this over, I'm going to move this over until I get to right over here. Right there. Okay? So here we go. We're going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right, I've moved that over 23 times to the left, right? That's how I got this 23. That's where that exponent comes from. So it means that I have 6.02, and then I move this over 23 times. And I fill in all the movement, all those little bubbles with zeros, right? Okay. All right, so that's how I would write that value. What about this value? This, the number of grams of gold that one atom has. All right, so if I wanted to write this value is 32.7 times 10 to the negative 23 grams. All right, where did I come up with that value? Well, it's the same concept. I'm going to move it over here, and you could move it to right here, but yeah, whatever. We're moving it to 32 like this because that's how we report when we're talking about grams, but you don't have to know that right now. Anyway, I'm just telling you, we're going to move it over to 32. okay? So it's in front of or behind the we only have 7 on the right of the decimal is what I mean. Okay, so we're going to do the same concept. We're going to move this decimal point over until it's right here. And if we look at that, if we do the whole thing, I'm not going to count it all out again. If we do the whole thing, we'll see that we move that decimal place 23 times. And the reason that it has a negative sign here is because this whole number is less than 1. All right? So let's look at a couple more examples. So when we have two different, you'll notice with these two examples, we have a positive value and we have a negative value. So let's talk about that really quick. So when we have values that are greater than 1, we are going to have our coefficient times 10 to a positive exponent. When we have values that are less than 1, we will have our same thing, our coefficient times 10 to a negative value, or a negative exponent. Okay? So, when we have, sorry, I forgot to write 1 there. When we have values that are greater than 1, the exponent is going to be positive. When we have values that are less than 1, the exponent is going to be negative. Some examples, let's do greater than 1 first. If I wanted to write this value in scientific notation, I would take my decimal, move it over 1, 2, 3, and we'll say 4, because I'm not, this will make sense how we know to go either here or here. That will make sense once we cover significant figures, but for now, we're just going to go until it's 1 digit. So we have 3.56 times 10. How do I know if it's negative or positive? Well, this value is greater than 1. Therefore, that means we must have a, what did I say it was? 1, 2, 3, 4? Positive 4. Not negative, positive 4 up there. Another example, let's look at 120. How do I write that in scientific notation? Well, I would move this decimal over 2 spots. So I have 1.20, if you want, times 10 to the positive 2 or negative 2. Well, this value, 120, is greater than 1, so it will be times 10 to the positive 2. And finally, what about this value? 4.55 times 10 to the positive 9. Is this value greater than or less than 1? It's greater than, and in fact, it would be 4, 5, 5, 0, and then 1, 2, 3, 1, 2, 3, like that. And to double check, you can count backwards from here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right, so that's how we write scientific notation with the positive exponent when we have values greater than 1. Values less than 1, for example, if I wanted to write 0.0008, how would I write this in scientific notation? I would move this over 1, 2, 3, 4, and I would get 8.0, or just 8, you don't even have to write 8.08 times 10 to what? 1, 2, 3, 4. But is it a positive 4 or a negative 4? Well, 0.0008 is less than 1. Therefore, this must be a negative 4. All right? And let's do one more example. We have 0.000073. All right, how would I write this in scientific notation? I would move this over 1, 2, 3, 4, 5. We have 7.3 times 10 to the negative 5 or the positive 5. Well, this is less than 0. Therefore, it would be times 10 to the negative 5. All right. Okay, let's see how much time we have left here. All right, our last rules, we have some rules for multiplying and dividing and for adding and subtracting when we're using scientific notation. So first we're going to look at the rules for multiplying and dividing. So first rule, multiplying. When we are multiplying with values in scientific notation, for example, if I have 3 times 10 to the 4 multiplied by 2 times 10 to the 6th. There is a special rule for this. We can't just, what do we do? We could multiply this part and this part, but what do we do about the exponents? When we are multiplying or dividing, when we're multiplying, multiplication with scientific notation, when we're doing multiplication with scientific notation, we multiply the coefficients, meaning these numbers, 3 and 2. We just multiply them like normal. And then we add the exponents, meaning this and this. So another way to write this would be 3 times 2, multiplying the coefficients, and then we're going to multiply that by 10 to the 4 plus 6. All right, we add the exponents. Okay, so our value that we get for that is 3 times 2 is 6, times 10 to the 4 plus 6, which is 10. There's our answer. Let's do another example. All right, so here's our example. 2.1 times 10 to the 3rd times 4.0 times 10 to the negative 7. All right, first of all, we see that we have 2 sets of numbers written in scientific notation. We see that we're multiplying here. So we should say, all right, immediately I know that I'm going to just multiply my exponents as usual, equals 2.1 times 4.0. But then I'm going to add, I said exponents, I think I said exponents, I meant coefficients, sorry. These are coefficients. Then we're going to add our exponents here. So we're going to have 3 plus negative 7. All right? So if we put, well, you should be able to figure that out. That is 8.4. No, 2, sorry. No, 4. What am I? I'm losing my mind. It's late. 8.4. And then we have times 10 to the 3 plus negative 7. So 3 plus negative 7 is negative 4. All right. So there we go. So that's pretty simple. When we're multiplying, we just multiply the coefficients, the numbers we have here and here, multiply the coefficients, and then add the exponents. All right? Okay, then we have rules for division with numbers written in scientific notation. The rule for division is that we divide the coefficients. So rather than multiplying, we divide, obviously, because we're dividing. Divide coefficients and subtract the exponents. All right. So let's look at some examples. It's the exact opposite of the rule that we just did. So let's look at some examples of this. We have 3.0 times 10 to the 5 divided by 6.0. That one's a little more challenging. Let's do 1.0. 1.0 times 10 to the 2. Okay? All right, so what we're going to do first is we're going to divide the coefficients. These are the coefficients. So we have 3 divided by 1 times 10 to the exponents. And we're going to subtract the exponents. And we're going to subtract the numerator from, the denominator from the numerator. So we'll have 5 minus 2. So if we look at that, that is 3 times 10 to the 5 minus 2, which is just 3. All right, another example. Let's look at another simple one. 8.0 times 10 to the 6th divided by 4.0 times 10 to the 1, or 10 to the 2. Let's not do 2 again. 4. Okay. So 8.0 times 10 to the 6 divided by 4.0 times 10 to the 4. That is going to equal our coefficients divided by one another, 8 divided by 4. And we're going to multiply that by 10 to the 6 minus 4. So this gives us 2 times 10 to the 2. All right, there's our answer for that one. Okay. That is where I'm going to stop today. If you want to add and subtract numbers in scientific notation and you aren't using a calculator, then we have to make the exponents the same. So I'm not going to focus as much on adding and subtracting exponents again because it's not, we're going to do it, but I'm just going to spend 5 minutes tomorrow doing it rather than explaining it right now. So your homework is to do the scientific notation practice problems. And that is it. We'll finish just with the quick rule of adding and subtracting tomorrow. And then we will move on to significant figures tomorrow as well. All right, please let me know if you have any questions. You can work on the practice problems for the rest of the period, and they will be due tomorrow before the start of class. Thank you.